Hey guys, my name is Rebecca Spees. I attend FGCU majoring in environmental studies as a senior. I'm in the environmental chemistry class with Professor Abercrombie, and we're going to talk about the pollutant polychlorinated biphenyls, but you may also know them as PCBs. PCBs belong to a broad family of man-made organic chemicals known as chlorinated hydrocarbons. They consist of carbon, hydrogen, and chlorine atoms. The number of chlorine atoms and their location in a PCB molecule determine many of its physical and chemical properties. There are 209 different congeners, and about half are responsible for environmental contamination. Roughly 36 are prevalent and potentially toxic. Only 25 are responsible for wildlife contamination, but the most toxic are those that have chlorine in the wing positions. They have no known taste or smell and range in consistency from thin, light-colored liquids to yellow or black waxy solids. PCBs were domestically manufactured from 1929. Due to their non-flammability, chemical stability, high boiling point, and electrical insulating properties, PCBs were used in hundreds of industrial and commercial applications, including electrical heat transfer and hydraulic equipment, plasticizers in paints, plastics, and rubber products, pigments, dyes, and carbonless copy paper. Under the Toxic Substances Control Act of 1976, all uses of PCBs were banned with certain exceptions. The exceptions included enclosed activities such as certain electrical equipment of authorized use or exempted use under a special petition. These uses or activities were allowed because EPA had determined that they provide no unreasonable risk to human health or the environment. In general, the materials containing PCBs at less than 50 parts per million are considered non-PCB items by EPA and are not regulated under the Toxic Substances Control Act. The human health effects of PCBs were first formally documented in the Yu Shou and Yu Chang incidents in 1968. It involved more than 1,600 individuals ingesting rice oil contaminated with PCBs. Reported health effects of those exposed included acneiform dermatitis, hyperpigmentation of the skin, aches and pains, peripheral nerve damage, and severe headaches. The children born to affected mothers showed similar effects, in addition to decreased birth weight and impaired intellectual development. Although PCBs are no longer commercially manufactured, there are several potential sources for continuing environmental releases. These sources include continued use and disposal of PCB-containing products such as transformers, capacitors, and other electrical equipment that was manufactured before 1977, combustion of PCB-containing materials, recycling of PCB-contaminated products such as carbonless copy paper, and releases from PCBs from waste storage and disposal. Humans and wildlife can be exposed to PCBs either directly from contact with contaminated air, sediments, or water, or indirectly through their diet. PCBs biomagnify and bioaccumulate.
But where do these chemicals come from, and how did they get here? In a phenomenon scientists call the grasshopper effect, toxic pollutants released thousands of miles to the south evaporate in the warm climate, then ride the winds until they reach the cold air of the Arctic, where they eventually fall to the earth. It doesn't take long for the caribou to feed upon the tainted moss and shrubs of the tundra. And in the sea, fish feed upon toxic plankton, which are then eaten by seals and polar bears.
To perform gas chromatography, often called GC, we use a gas chromatograph. A gas chromatograph is an instrument with a long column filled with small particles coated with a very thin layer of an adsorbent. This layer is the stationary phase of the column. Helium runs through the column and is the mobile phase. A sample injected into the gas chromatograph is instantly vaporized in a heated injection chamber so that the components are in the gas phase, and then it flows through the column. The helium is the carrier for your sample. This technique allows us to separate volatile organic compounds based on their physical properties and determine relative amounts of product yields. Coupled with a computer library, GC can also be used to identify organic compounds.